Okay, so today in this video, we're gonna talk about graphing. And there's three things that we're gonna talk about. One thing is identifying the independent and dependent variables and explaining where they go on the axis. What goes on the y-axis, what goes on the x-axis. Second thing we're gonna do is talk about how to draw your axes to scale. So you make sure that each box along an axis has the same value. If it doesn't, then there's no point. Okay, and then the third thing we're going to talk about is choosing the appropriate graph. Okay, so here we go. And again, we're talking about graphing. And the axes are going to pop up here. The y-axis is the vertical one, the x is the horizontal. And the two variables we're going to be talking about are the independent and the dependent variable. Okay, these are the two things you really need to identify in an experiment. Okay, so the independent variable we've seen a lot of examples of in class. All right, and the independent variable is the thing that you are changing. The temperature. Putting in the pretzels, or I'm sorry, adding pretzels more and more each time, increasing the substrate concentration, adding toothpicks to model the competitive inhibitors. Okay, changing the pH. Whatever it is, it's what you're changing. Now we need to be really careful that there's only one thing that we're changing. If we change the temperature and we also change the number of pretzels each time, we don't know what's causing the effect, right? So you'll see what I mean in a little bit. We're going to do a specific example here. The other variable that we need to talk about is the dependent variable. And that's always the thing that you're measuring to see the effect of the independent variable. So in the case of the Pretzelace lab, right, we had temperature, we had substrate concentration, whatever it was, we were measuring the number of pretzels we broke to see the effect of the change we made. So I hope that makes sense. Today, what we're going to do is take this idea of competitive inhibitors. Okay. Now, at the bottom I wrote concentration of competitive inhibitors. So what this means is that we are leaving the number of pretzels the same each time, and we're going to add more toothpicks each time. So the number of toothpicks, the concentration of toothpicks, the concentration of competitive inhibitors is going to increase. Okay, and what we want to do is see the effect on the reaction rate. Is it going to slow down the reaction? Is it going to speed up the reaction? It's really important that we leave the number of pretzels the same in each trial and just increase the number of toothpicks. Because if we increase the number of pretzels and we increase the number of toothpicks, then we really don't know what's actually causing the effect, what's causing the reaction rate to do what it's doing. That's bad science. We have to do one independent variable at a time, and we have to keep everything else constant. If we don't do that, then the experiment's meaningless. So we're trying to avoid that at all costs. Okay, but what we measure is always the dependent variable. So you can see down below that we put the independent variable, the thing we're changing, on the x-axis, and we're going to put the dependent variable, the reaction rate, and again our units for reaction rate are going to be the number of pretzels broken per second. Okay, so that's a rate, something happening over time. So we're getting a number there. What you'll notice is that I only wrote units down below. Okay, concentration is measured in units, and you're going to learn all about that in chemistry. So I'm not going to talk about it here, but I just want to let you know that you would see some kind of units down there. Okay, so here we go. What you're going to see come up now is a red line. Okay, and that red line is representing what happens as we increase the number of toothpicks but leave the number of pretzels the same. Okay, if there's very few toothpicks, so if we're on the left side of the x-axis, then what's going to happen is we're going to be grabbing more pretzels and we're going to be able to break more pretzels per second. If we keep adding more toothpicks, we're going to grab more toothpicks and less pretzels, and so the number of pretzels we break is going to decrease over time. Okay, so that is the difference between independent and dependent variables, and make sure you know which axes they go on. Alright, Hope you like that one, and here comes our next slide. Okay, and in this one, we're going to be talking about how to draw an axis to scale, or draw the axes to scale. Again, we got our y-axis, and we got our x-axis. I'm going to speed this up a little bit. Okay, and what we're going to do is we're going to draw a little data table on your right here. It's going to come up in a moment, and it should look familiar because it's what we did in the Pretzelace lab, right? We tested the effective substrate concentration by adding more and more pretzels each time. Again, leaving everything else constant except for the number of pretzels that we're adding. Okay, so there's our data set, and we'll notice we have two sets of numbers, and that's important for later on. We added more and more pretzels each time, and we see somewhere between 30 and 40 if we only had one enzyme, right? We didn't want to add more enzyme because then we wouldn't know if it's the enzyme or the pretzels that are affecting the reaction rate. So we stuck with one enzyme. The enzyme concentration stayed the same. The substrate concentration was increasing. So again, that's our independent variable, so that's going to go on the x-axis, and the dependent variable, the number of pretzels broken, is going to go on the y. Okay, now what we need to do is identify the highest value for each set of numbers, right? Each set of measurements. And so if we count, let's count 20 squares across, and we'll put the number 60 at the 20 square mark. All right, and then we're going to go ahead and number them. So I'm going to show you the math I did, the simple arithmetic I did, to decide how much each square was worth. Right? I've got my highest value is 60. I've got 20 squares along my x-axis that I'm using, and so I'm going to divide 20 into 60, and I get 3. And so each square has a value of 3. I got lazy and I started skipping some along the way, but the x-axis is to scale. So we're going to go ahead and label it. You've got to make sure you label your axes. That's another really important thing. Okay, if you don't label it, we don't know what the numbers are, and your graph is meaningless. Trying to avoid that. Okay, so again, we got our units down there, number of pretzels, and then the dependent variable is going to go along the y-axis, and we're measuring our reaction rate again, and again, that's a function of how many pretzels we broke per second. All right, and then we're going to go ahead and number the y-axis. And our highest value is 37, so what I did to make it easy on myself is I bumped up to 40, and I made the boxes each worth 2 because I divided 40 by 20, and then I went ahead and plotted my points and drew in the line to show the trend, to show the relationship between increasing the number of pretzels and what it does to reaction rate. We can see right around 37 that the graph levels off. And after a point, it doesn't matter how much substrate you take in. It's the reaction's limited by the number of enzymes. Okay, so that's drawing our axes to scale. I hope that one made sense for you. And now we'll talk about which kinds of graphs we should choose for certain kinds of data. Okay, so choosing the right graph. We need our axes again. Got our x and y. And now we're trying to decide between a line or a bar graph. And all you really need to do is look at the kind of data you have. Okay, so there's going to be two different things. One group of data is going to have two sets of measurements. Okay, that's what we saw in the last one. Or you can have one set of measurements and one set of qualitative data. So I'll give you an example of qualitative data in just a moment here. Okay, we're describing the quality of something. It's not a measurement. There's no numbers involved. So if we have two sets of measurements, we're going to use a line graph. And if we have one set of measurements, one set of numbers, and one set of qualitative data, we're going to do a bar graph. And we had a really good example of that again in that Pretzelace lab, where you measured the number of pretzels you broke as a function of temperature. But the temperature was measured not in numbers. It was measured by describing it. We had a cold, we had a room temperature, we had a hot. Okay, so those are not numbers, right? So we can't, there's no way to make our x-axis to scale. We're just going to reserve the same amount of room for each of the bars to just kind of keep it organized. All right, but again, the bar graph is when you have one set of measurements and one set of the qualitative data, and the line graph is when you have two sets of measurements, exactly what we saw in our last slide. Okay, so let's finish this up, and we'll label our x-axes with the different temperatures that we described. Again, they're words, not numbers. And then we've got the number of pretzels we broke as a function of temperature, right? And so what we saw, and again, there's no units for temperature because we weren't measuring anything. We were describing, but the reaction rate, we were still measuring something, the number of pretzels broken per second. Okay, and when we draw our bar graphs, when we draw on our bars, right, we saw that we see that the cold, we had a much slower reaction rate than we did at room temperature, and I'm just taking the number that we had from the last slide for room temperature. Around 37 was our max, and then at hot we remember that enzymes get denatured, right? So they're not going to work as well. So when I taped all your fingers together, you were unable to break pretzels as effectively, and your reaction rate decreased. So I hope this helps. Again, this is just a quick review of graphing, and I wish you the best of luck on the test tomorrow. So again, good luck, and let me know how you like these. Take care. Have a good night.